Can a tiny fungus growing quietly in the Amazon really save us from plastic pollution? Every year, the world produces over 300 million tons of plastic, and most of it isn't going anywhere. It just sits there in landfills, rivers, and oceans. One of the toughest plastics to deal with? Polyurethane. You'll find it in mattresses, car interiors, surfboards, even insulation panels. Polyurethane is built to last. Its chemical bonds resist breakdown. That's great for products, but terrible for the planet. Some PU stays intact for hundreds of years. Landfilling takes up land and traps waste underground. Incineration releases toxic gases, and less than 15% of PU ever gets recycled, usually into lower-grade products. But in 2011, a group of Yale undergrads found something unexpected in the Amazon's Yasuni rainforest, a humble fungus. Pestalotiopsis Microspora. First described in this role by Jonathan R. Russell and his team from Yale, published in Applied and Environmental Microbiology in 2011. Sounds like science fiction, but this fungus eats polyurethane like it's breakfast. It's not just breaking plastic down, it survives on it. PU is its only source of carbon. No sugar, no sunlight, just plastic. And here's the kicker. It works without oxygen. That means it can keep munching away even deep inside a landfill. The secret? Enzymes like esterase and serine hydrolase. These enzymes snip apart the tough ester bonds that hold PU together. Those long polymer chains, broken into small digestible molecules. The fungus turns them into biomass and maybe even usable compounds. With its filamentous body, the fungus grows into the plastic, increasing surface area, forming cracks, and accelerating decay. Scientists are exploring biotech systems, combining Pestalotiopsis with other microbes to tackle different types of plastics. But there's a catch. So far, this fungus works mostly in labs. It takes months to degrade small samples. Scaling it up is still a big challenge. If released carelessly, it could become invasive, disrupting ecosystems, outcompeting native fungi, or breaking down the wrong materials. And what about the leftovers? Are the byproducts of PU degradation truly safe for wildlife and humans? We're still figuring that out. So, researchers are tweaking the genes, testing fungal cocktails, and engineering reactors to make this work faster and better. Another idea? Use the purified enzymes directly. Custom fit them into waste facilities to break plastic without the whole fungus. Maybe someday, every home has a mini compost bin with fungi designed to break down what we throw away. A small fungus from the rainforest might be one of our biggest tools against plastic waste. But we'll need more. Less plastic use, better design, and serious policy change. The fungus is a start, not the whole solution. The future of plastic might not be in a landfill, but in biology. Maybe the answer has been growing quietly all along. A planet drowning in plastic, and a fungus quietly waiting to clean it up. Will we give it the chance?